Hello, everyone. Welcome to our webinar today. And today we're going to be focused on block forces and frequency-based substructuring. And our colleague, Patrick Corbel, is going to be joining us to discuss this topic with us. Patrick's a product manager. And before we get started and give our attention to Patrick, I just wanted to highlight a couple more webinars that are going to be taking place in this series. We started off the series, we were talking about FRF acquisition techniques, and we talked about the importance of having very accurate FRF data for our virtual prototype assembly tool. And today we're going to be focused on block forces, what those are, and how frequency-based substructuring can be very useful to us. We're going to be talking about importing simulation data, specifically with Simcenter 3D. We're going to be talking about some practical considerations for testing and performing this component-based analysis. And lastly, some hands-on time with the actual virtual prototype assembly tool within Test Lab. Just wanted to give a kind of a brief overview. What is virtual prototype assembly, or we say VPA, it's the acronym we use for short. Well, it's a process that allows engineers to predict system, or in the case with this slide, with this example, vehicle level NVH performance from component level data. Components are independently characterized as component models using component-based transfer path analysis. And this component data can be generated via testing, as you can kind of see here, but it's not necessary or mandatory always to have a prototype. It can equally be done with simulation or on a bench test. And once we have these component models, they're in a standardized format such that they can be shared and reused between test and CAE teams, or even non-experts for analysis, maybe those who are just focused on performance metrics specifically. So basically, these are the 4 steps. We want to characterize our sources, for example, maybe an electric motor, our receivers, the things that our sources are connected to, maybe it's, it's electric motors installed in one of these vehicles. Once we have the data, we want to store it in our component library, and then we're going to basically be able to virtually assemble them, predict the overall system level, vehicle level NVH performance. And lastly, it has a lot of different applications, not just automotive, but it could be aerospace, it could be ships, a number of different applications we can use this tool to predict system level NVH performance. Now we're going to give our attention to Patrick now. He's going to be talking to us today about block forces and frequency-based substructuring. Patrick, let me switch over to give you control.
So Charles, thanks for the introduction. As Charles has mentioned, so this part will be a bit about the methods that run behind VPA that enable this system NVH prediction. So the big focus there is how to characterize independently these sources, so there are quantities in place like blocked forces and so on, and also how can I then, once I have characterized these sources, how can I do predictions? So that's where frequency-based substructuring comes in. Before I jump in, just some introductory slides just to show you the capabilities. So why do we want to do these NVH predictions? So I just take here an example. So imagine you're a manufacturer of a steering system, like you can see in the picture. Often, only at the very end of the development cycle of a vehicle, you will be able to get a prototype as a supplier to be able to test how this steering system will perform in the vehicle. And sometimes it will be good, sometimes maybe there could arise some issues, and then you have to do some very expensive late troubleshooting actions to make sure that the noise and vibration is acceptable in the vehicle. So as a supplier, it could help you a lot if you could front load this evaluation. So if you could do this evaluation on vehicle level without having to rely on a physical vehicle prototype. This will help you also to discuss targets for the integration also on your components. One technology that could help with that, as already mentioned by Charles, is this component-based transfer path analysis. What do we do there? As you can see on the picture on the left, independent of the vehicle on a test rig, we try to characterize the steering system. We do that by trying to estimate a quantity that we will explain later that is called blocked forces, because it's independent of the test rig and can be used then once we have some transfer functions from the vehicle to do some predictions on vehicle level. Once you have characterized these components, so for example, you have several steering systems, you have several vehicles where you want to do predictions on, then you have a lot more capabilities. Just an example to highlight that before I jump into the theory. Just to show you the benefits of implementing this process. So imagine here I have another example. Imagine you have to integrate an airco pump, an HVAC pump inside the vehicle. If you don't have the vehicle, maybe it doesn't exist yet. Maybe you only have it in simulation. And so maybe a question could be, what is the optimal position to integrate this from an NVH performance point? If we implement this process, so imagine you have characterized, or from a supplier you get the blocked forces. So you have a first component that is characterized. This pump is connected, integrated via a rubber mount, where you have stiffness for. Maybe there is a bracket to integrate it, where you have some transfer functions from simulation or test. And then you have the transfer functions of the actual vehicle, the body. Once you have that, as Charles has explained, you can put them in a database and you can play with it. So that's just to show you what you can do then with this process. I'll just show a short demo in the software. Here you can see the different components. You have on the right, you have the vehicle pump. So these are some transfer functions, but also these blocked forces. You have the rubber element, you have a bracket, and you have the vehicle. For the first position, you have the transfer functions. So in the software, once you have all the data available, you can very fast do some what-if analysis. So as you can see here in the picture, we can create a first assembly, then replace the vehicle with the transfer functions for the second position. Then we can go for even a third position. We add it to all the assemblies. Maybe you have also from simulation an adapted bracket. So we load it in there. And then we have 4 assemblies now already created in this short moment. And then you can just hit the run button and all the noise predictions will run for the 4 assemblies. And then you will get a result like you can see here in the image, where you can say, for example, for the driver's ear, what is the sound that is produced by this pump if I would integrate it in this vehicle on this position. Here we compare position 2 and 3. You see, for example, immediately from this picture that position 2 has a much more higher noise levels than position 3. So in function of RPM, I see here the different spectra, and I can check them here, and I see already that the frequency is at a much higher level. It gives you a very easy way to evaluate these different positions and make decisions using these predictions. Next to looking at it, also in Simcenter, we can just listen to these predictions. I will not go in detail to that, but just that you're aware of. So you can check these results in frequency, but you can even also listen how this pump would sound inside the vehicle. To be able to enable this process, like I explained, we need several methods. So a little bit of theory. So the first thing, we need techniques to characterize these noise sources independently so that we can use them later on in a modular way. So there come quantities for structure born, for example, like these blocked forces. And then in a second step, we want to do these predictions, and that's where frequency-based substructuring comes in. So that allows you, from multiple components, you have representative transfer function data, you can create an assembly and calculate how it will behave when it's assembled. All these methods that I will show are integrated in the software that you just saw, the virtual prototype assembly software. I will just take a step back and explain. I will start from the classical transfer path analysis, so the source transfer receiver approach. Probably quite some people that are attending are familiar with the classical transfer path analysis because it's also often used to evaluate the noise performance of a certain component inside the vehicle or any other system. Yeah, I use here now the vehicle, but these methods can be applied on any type of application. So what do we do there to evaluate the noise and vibration performance of a certain noise source? So for example, if you have the engine inside the vehicle, what we want to see, if there is a disturbing noise inside the vehicle, we want to see how this energy is traveling from the engine to the driver's ear or to the seat that is vibrating. And to be able to do that, you could do a classical transfer path analysis. First step in a classical transfer path analysis is that we estimate the loads that are traveling from the engine so that the engine is applying to the body. The engine is maybe suspended with 3 mounts. In every of these mounts, we estimate the load, so the interface forces that are between the engine and the vehicle body. Once we have that, we can multiply each of these forces with the corresponding noise transfer functions, and we get the contributions to the driver ear. A typical result you can see here on the right top, for example, in function of the RPM of the engine, you see the contribution of each of the parts. Here we can see we have maybe some high level for this body 8X, which is maybe the anti-roll mount, and then we know this is the most contributing part. If we want to change something, improve the noise, we have to work on this part, and then we can check is it the transfer or if it's the source we have to work on. This is a classical TPA. If you do it in test-based, you need to have the full vehicle available. That's the way it works. And so we have to see if we have to adapt this classical TPA to be able that we can also use it without that we have the full vehicle available. Just to summarize, how does this classical TPA work? So typically, if we have a structure-borne noise source that is acting, there is some interface that we define between the source and the receiver. And on this interface, for structure-borne, we want to identify interface or contact forces. So these forces generate the same vibration pattern on the receiver as if the source would be present. So they represent essentially, if we would remove the source and we would put in place these interface forces, they would generate the same vibrations and noise in the receiver. Different techniques in classical TPA that we use to identify these interface forces. The most common ones are, let's say, mount stiffness method, for example. If it's a soft connection, if we know the mount stiffness of this connection, we put an accelerometer on the active and on the passive side of the connection, and combined during operation, we measure these vibrations and then we combine it with the mount stiffness to calculate the interface force. Another common method that can be more used for all kinds of connections is the matrix inversion method, where we put accelerometers on the passive part, so on the receiver side. We measure them during operation, and then we remove the source. So we have to remove the source, and then we measure the transfer functions between the connections and these accelerometers. So then you build up this matrix that finds a relation between the force and the responses. If we invert them and combine them with the measured accelerations, we can find these interface forces. There are also more advanced methods like OPACs. Also for airborne, there are specific methods to get the airborne loads. I just show this as an introduction because now we have to modify this method, because for our purpose, doing really NVH predictions on other systems, it seems to be that this method is not suited. So imagine that you get the interface loads, for example, from a test bench for this electric motor. If we then want to do a prediction on a certain receiving vehicle, we will see that our prediction in general will fail, because these interface forces, they do not only depend on the source, but they also depend on the receivers, or they're not independent of the test rig that we use, for example. So we need another quantity, and there where this component-based TPA comes in. So we want to identify, for example, blocked forces or free velocities on a test bench. As I mentioned, interface forces in general, they cannot use it for advanced what-if analysis or predictions. So we need independent load characterization. For structure-borne, we look then at quantities like blocked forces or free velocities. And for airborne, we typically assume the Coulomb velocities can be used. Today I will focus mainly on the more complex part, which is the structure-borne, where we have to look at these blocked forces and free velocities. How does it work? What are these blocked forces? Essentially, it's the force that we would measure if we clamp really every connection between the source and the receiver. You see here on the left. The interface force that you would measure then is the blocked force. So if there is no movement anymore allowed in the connections, theoretically, if you could clamp really your source that there is no movement in the connections, the force that you would measure, that's what we call the blocked force. So while it's operating, we assume then that the source mechanism is an ideal force mechanism or an ideal displacement source. And then once we have this blocked force, when we apply them on the full assembly, we get good predictions for the receiver, and we can even modify this receiver. So that's the advantage of these blocked forces. What are now the ways to identify them? Yeah, the first you can see here, people really build blocked force test rigs. So test rigs that are very stiff in the frequency range of interest compared to their source. And so they can, with force cells, directly measure the blocked force. Just to prove mathematically, I also write here shortly the simple equations. Why is this blocked force? Just to prove that this blocked force is independent of the receiver and only relying on the source. So I note down here for this source, the equations. So for example, we have a response point U2 at the connection. This only depends on the blocked force and on the internal force that is in a certain source. We can see that. So I wrote down the equations. If U2 is clamped, we can reformulate these equations. We know that F, the interface force that we measure at 2 is the blocked force. And we can see between the internal force and the blocked force, there is a direct relation that doesn't depend on any receiver. So we know now that the blocked force only depends on the source mechanism. And just some examples, there are many. I've seen also for all kinds of engines, electric engine, combustion engines, even powertrains, people building blocked force test rigs. But here you see some examples, for example, for a tire wheel. So we have the tire wheel running over some kind of road profile. We have a very stiff test bench, and at the center we have a force cell that measures in the 6 DOFs the forces and moments, so the blocked forces and moments. So that's a direct measurement that is performed here. This is an automotive example on the right. To have a different example, you see also for satellite components, this is often used. So we have a gyroscope that is used to position the accelerometer. They can cause vibrations, what they call micro vibration, and so for sensitive measurement or equipment on the satellite that's not wanted. So these suppliers also always have to measure the blocked force. So they put this gyroscope on a direct blocked force cell measurement test rig. They also measure here in 6 degrees of freedom the blocked force. So once you have that, you can go to a next step for the predictions. Just to give you a bit of feeling on what this blocked force actually is, I found this an interesting picture here on the right to explain a bit what a blocked force is. Imagine you have a source that is connected to only 1 DOF to a receiver, and you see here the ratio between the stiffness of the source versus the receiver. So if the receiver is very stiff, you're in blocked condition, and when the receiver is very soft, it can move freely, the source. For the 1 DOF case, we know that if the stiffness of the source and the receiver is very similar, then you get maximum, you have the worst case, so you have maximum power transfer from the source to the receiver, so that's typically not wanted. But just to give you an idea about the differences between blocked force and interface force, if the receiver has a certain stiffness compared to the source, you get interface force that is different. If we make the receiver more stiff, we slowly merge towards the blocked force condition. Another procedure, so blocked force is, like I said, good description of the source because it's only relying on the source mechanism. Another quantity is, of course, here on the right, when the source is moving in free, and that's what we call free velocity. So also free velocity can be used to characterize independently your source. What is this free velocity? If you can suspend your source really in free conditions so that the vibration of the source is not affected by any receiver, vibration we measure in the connections is actually the free vibration or the free velocity. Again, there is a direct relation between this free velocity and our source mechanism. If we write down the equation just as before, we can see this free vibration is a direct relation towards the source mechanism. And if we combine it even with the equation before, we can see that you can also, once you have the free velocity, you can calculate out of it your blocked force again. So for components that are typically softly suspended, this free velocity could be a good alternative instead of a blocked force to characterize your source. You just have to make sure that its stiffness of your source is 10 dB more stiff than your receiver, so that it's approximately this free condition. You put in your connection accelerometers and you can capture the free velocity or free acceleration. Of course, for a lot of applications, it's not possible to create test rigs that accommodate that, so that are very rigid or very soft. There is also an alternative method where there is no requirements for the receiver almost. So the receiver can be a certain test rig, but it can be also in your system, in your vehicle, you can characterize your source. And that's what we call in-situ TPA. How does it work? It's very similar to the matrix inversion TPA, classically, that I explained. There is only actually one difference. So we run the source installed on this receiver. We measure the vibration, so we put some indicator accelerometers on the receiver. So then we get this A4. Then we stop the source, and without removing the source, we measure the transfer functions between the connections and these indicators. The difference is that we measure these FRFs while the source is still present. And then in 2008, in a paper of Elliott and Morehouse, they discovered that when you do this, you will get actually the blocked force instead of the interface force. So the calculation is exactly the same as the matrix inversion for classical TPA, but here we use the full assembly transfer functions. Of course, we apply here matrix inversion, so you have to really take care of your FRF data quality and monitor the conditioning of your matrix inversion. If there is noise on the data, you get errors on your estimated blocked forces. Just to prove that, this equation. Just look on simulation side where we have no noise and so on. It's very easy to do. We took, for example, an engine which is mounted on this vehicle. We modify the mount stiffness, and we can see here on the right that the interface force that we would capture from classical TPA, so the force going through these mounts is varying a lot with the mount stiffness, whereas we would apply this in-situ TPA, so this matrix inversion using the full assembly FRFs, we see that we always find back the same blocked force that is only affected by our source. So any modifications to mounts or receiver doesn't affect these blocked force, and also that's what we want, because we are looking for an independent source descriptor. That was simulation. Also industrially, this works. I take again the example I've shown before. So for example, if we take the tire wheel on a tire wheel test bench. So also here, you could measure the blocked forces directly, but we also applied on this test rig this matrix inversion technique. And we could prove that these blocked forces are really independent of the test rig. So we measured for this wheel set these blocked forces on this test rig. And then we replaced the test rig with the actual vehicle you see in the picture. We run the vehicle with the same, on the test rig, we had the same preload, the same speed, and then you get the same blocked forces. For interface forces, this would definitely be not the case. Just to be complete, of course, also mathematically, we can prove this so that this equation holds. To be able to do that, you have to write structuring equations for the two systems. You have the source system, you have the receiver system, and if you combine it with the equations I've shown before for the blocked force, then you get a relation between blocked force and interface force, and blocked force and the predictions you would do, and the vibrations it would cause on the receiver. And if we apply then a frequency-based substructuring. But that will come later on. Just for completeness, I show here these equations so that prove that mathematically we also come to the same conclusion, that we can get the blocked forces with measurements on any type of receiving system. So just to highlight the difference, so for people that are familiar with classical TPA, what are the differences now with this in-situ matrix inversion technique, where we get the blocked forces instead of the interface forces? So the big difference is during the FRF measurement step, where we measure the FRFs between the connectors and the indicator accelerometers we have. So for classic TPA, we have to remove the source during these FRF measurements. For in-situ matrix inversion TPA, we have to keep the source in place while we do these FRF measurements. So that's the difference. Operational measurements are exactly the same. We just run the source in the typical operational conditions. We measure the accelerations of the accelerometers on the receiver. The force identification calculation is the same, but we use different FRFs, and because of that we get a different results. So for classical TPA, we get the interface forces, the actual forces in these connections, where for in-situ TPA, we get the blocked forces as if this source would be clamped in these positions. So the results have to be interpreted quite differently. To highlight this, so the entire process that I've shown, measuring these FRFs, doing the operational measurements, and then doing the calculations, and even do the next steps, the contribution analysis and the predictive analysis. So all these steps are fully supported in our test lab platform. So you can do the measurements with our FRF testing applications, those are signature applications, and then you combine these measurements in our transfer path analysis application, where you will calculate either the interface forces or the blocked forces. Just as a quick demo, I will show you how easy that is, this calculation. So imagine you have done the FRF measurements and you have done the operational measurements. How can you calculate in test lab quickly then these blocked forces? Just as a summary, so the process, people that are familiar with classical TPA is exactly the same. You just load a different FRF set. So I load the FRF set, I load the operational measurements, I put them in the input basket, and then I will run through the process. So typically test lab guides you through the process. First, we will create a TPA model. So we have to highlight which DOFs are the connections, which DOFs are now the targets where we will validate the blocked forces. Then we indicate what are connection DOFs where we want to identify the blocked forces, and then we indicate where we put accelerometers on the receiver. So this example is a small wiper motor that we use here, just as an example. Then I load operational data. Automatically it shows which FRFs are required for my calculation. And when I have all FRFs, everything is green, like in this case. And then the software shows me which operational data is required for this calculation. Now all data is loaded, the model is ready. I can go to TPA loads, where I will perform the calculation. I will use now all indicators, so I can just push create full matrix, and now my loads are calculated. So on top I see I've chosen to describe this source with 9 degrees of freedom, so I have 9 blocked forces calculated. A check that is often done is we have some accelerometers that are not in the model. This is what we call a target prediction or the onboard validation. So we check if the measured and the total for this target is matching. So then we have a first validation of quality of our blocked forces that we calculated. So in this case, I had data for several orders, order 10, 20, 30, and so on. I can check the quality of all of them individually. When I'm happy with them, I can just on the left bottom click the save button, and I have my results stored. Just to demonstrate you how easy it is to calculate in TestLab these blocked forces. And there is not much difference to the classical TPA matrix inversion. Just as a summary, the 3 methods that I've shown for structure-borne noise characterization. So on the left, we have the direct measurements, where we have dedicated test rigs, where we make sure that the receiver is more stiff than the source. Then we can use force cells to measure blocked forces. In the middle, for applications that are softly mounted, there we could make in certain frequency ranges approximations that the source is running in free, and so we can get the blocked force via the free velocity. And on the right, so there is less demands towards the test rig or to the receiver, but we have to closely monitor data quality that is required and also the condition of our matrix, because we will use matrix inversion to calculate the blocked force. This slide, I will be very brief. I just wanted to highlight that there are some ISO standards that you could follow if you want to do this source characterization. You have one related to free velocity. The newest ones are ISO 2270, which describes this in-situ method, so this matrix inversion method. So it helps you to can act as guidelines if you want to characterize the blocked forces and develop this process for your applications. So it's effective since 2019. And then there is also another one which is very similar. It's a 21955, which is effective since 2021. It's based on the same methods. It has a slightly different notation. It describes how you characterize, but it also will do an attempt on explain what are the best methods to predict for your case, do the predictions in the next step. That's what you see here. Okay, just as a summary so that you're aware of these ISO standards. Good, so this was the part related to noise source characterization. So once we have characterized our noise sources, we want to go to the next step and we want to do predictions, and that's where this frequency-based substructuring comes in. I will start here again with the example of the start with the steering system. So imagine I've used one of the methods just shown to characterize my source, maybe the In-situ TPA. I have my steering system on a test bench. I've characterized the blocked forces. Now you want to maybe see how this steering system will behave in a full vehicle. What do we need then from this full vehicle to be able to do these predictions? We need the coupled transfer functions between the blocked force attachment and the target. Can be the driver's ear, can be the seat vibration, depending on your application. Looking again at the automotive example. How can we measure this full assembly FRF? We have to put the mount steering system inside the vehicle and then perform this FRF measurement. So that's a possibility. If you have the vehicle available, you can use this way to get this transfer function. Of course, like I said at the start, it would be nice if we don't have to physically have the prototype available of the vehicle and we can calculate this transfer function without having to measure it. And that's where the substructuring comes in. So now I replaced here with a bit of a complex equation. I replaced here this coupled transfer function, but it's actually the way to calculate if I have FRFs from my steering system and from my receiver, I can calculate this coupled transfer function and do my prediction. And what we apply here is FBS substructuring to get this coupled transfer function. So once you have FRF data from your steering system and from your vehicle, the software will automatically in the back apply the equation you see here. Where does this equation come from? So that's one of the dynamic substructuring techniques. So it's a way if you have information from your subsystems to create the FRFs of your assembled system. If you have a physical component, you can characterize it in several domains. So by using transfer functions, or maybe you have mode sets, or you can have a state space model, and so on. Each of these domains you can do substructuring in. So you have FBS for FRFs, we have component mode synthesis if you have mode sets, and we have state space substructuring if you have state space models. If you have good models, the results will be very similar for all three. But we have a preference if partially the data is coming from test towards these FBS, because then we can use directly measured FRFs. So that's why we typically use this method. What does it require? So for example, if I have a subframe, I want to combine it with the body with some mounts in between, I need to have the FRFs between the coupling points and also the FRFs towards the target points where I want to do predictions. And then I can choose if the connections are rigid or flexible. What it will produce is FRFs of the assembled system. Here you see the equations. So we have FRFs of substructure A and substructure B. And what we want to have with FBS, we can calculate them using this equation. We can calculate the assembled FRFs. So they are noted here with A, B. So these are really the FRFs between all these 0.1, 2, and 4 of the full assembly. So these are actually the results I need to do my predictions once I have my blocked forces. How do we go from these equations to here? I will not go in detail here. So basically what we do is we define what are the connection points, and we write down the equations for force equilibrium. There we use this thing called the Lagrange multiplier. And also we cause a displacement. Of course, we say that the displacement of this connection of A and B has to be the same. The method, as you can see, allows direct use of FRFs, and we can optionally introduce also a flexibility or a compliance in the connection. What do you have to be careful if you use measurement data? We see again here this inversion. So if you have imperfect measurement data, you can have what we call spurious peaks on the results when you apply FBS. So the ref data quality has to be really high. So we apply methods like virtual point transformation, combined with also dedicated Q sources that you saw in the previous presentation to get really the highest quality of FRFs as input. And then there are also ways afterwards to clean up the FRF data, for example, symmetrization. So that's when we enforce reciprocity on the FRF data. And then there are some other options just in case if you have issues with your data set. Okay, just instead of looking at this bigger equation, I think I will just explain how we do it for the blocked forces prediction. So we have our steering system, we have our blocked forces. What do we see in the equation? We multiply it with the FRF matrix between the connections of the source. That means that we convert these blocked forces in a free acceleration. Then we combine it with what we call the coupling matrix, the FBS coupling matrix. And you see it's a sum of the connection FRF matrix on the source and the receiver. And essentially by multiplying this with this inversion and the free acceleration, we calculate the interface force that is required to close the gap between your source and your receiver. Now we have the interface force predicted from our blocked force, and then we can combine it with the transfer function of the receiver, just as in classical TPA, to get the noise contribution from our source towards the interior. And essentially what we calculated here is the coupled assembled transfer function. I will just highlight quickly the advantages and disadvantages of FBS, why that we use it. So we reduce the model. It's a performance model, not a design model, so we can do fast calculations. It's only based on FRFs. We can use it for low and mid frequency. It allows hybrid systems. So if one component is simulation, the other component is test, we can combine them. We can do fast what if, and it's of course complementary to our TPA calculations. And as mentioned, you have to be careful of noise issues on the data, and it's a non-parametric model. So if you want to change some parameters. The second step was this prediction, so that we've seen. Now, this is what I wanted to show. Now, what are the measurements you have to do for source A? As I explained, you have to estimate somehow the blocked force. And then what we need to be able to connect it to a receiver, you need to have the FRFs between the connection points. So typically we suspend it in free, and we measure the FRFs between the connections. So that's in theory the minimum what we need. And then for the receiver, we need FRFs between the connections and also the FRFs from the connection towards the target. And once we have that, we can do the predictions of this source and this receiver. And optionally, like I said, you can always integrate them out. What are application examples where we use this frequency-based substructuring? For example, if you have a transmission and a bracket, you can see if I modify this bracket, how will the transfer function be affected? For example, Road noise, that's example already shown. So we get the FRFs of the tire wheel and we connect it to the suspension of the vehicle. The HVAC compressor, so we get FRFs of that, we connect it to the body and we calculate the transfer. If you really take care of your noise and get high quality input data, then you get also very valuable results, as you can see here. So here the tire and the vehicle were measured separately. And then you see here the validation of the measured FRF when the tire was installed on the vehicle and the calculated one by FBS for rotational TOFs from the wheel center towards, and also for the translational TOFs towards the driver's ear. FBS, of course, doesn't only allow you to connect one source and one receiver. Your receiver can be really split in multiple levels. So we have, for example, here a tire set, we have the front and the rear suspension, we have the shock absorbers, the bushings, and then we have the vehicle body. So we have here the suspension really as a separate system. And to show you also here, you can, when you put high quality measurement and simulation data in, you get also very high quality predictions. I think this is another example. So here we applied the same for electric drive unit. So we have electric drive unit, structure-borne, airborne, bushings. It has 4 mounts. You have a rear axle carrier, against 4 mounts, and then the vehicle body. So here we calculate, and using this equation I've shown before, we calculate first the assembled receiver, then we apply the blocked force, and then we get the noise predictions inside the vehicle. Just as a summary, I think in the software that I've shown, all these methods are supported. So you can load loads as blocked forces, free velocities, but you can also simplify the methods and just apply direct loads. For some systems where we say there is strong interaction, you really have to work with blocked forces and so on, because there is strong interaction. The interface forces are really dependent on the receiver and the source. But for some applications, you can make some assumptions, and then we call them weakly coupled, and you can simplify the equation. So both types of sources are supported. That's for structure-borne. You can have airborne sources, and they can be characterized in any frequency domain format. So order, spectra, auto powers, 1/3 octave, and so on. And we can then create now any kind of structural assembly. So it can be one receiver, one source, but you can also make it more complex. And then the last thing, you can even run now operational scenarios. So if you characterize your source for different, like for example, if you have an engine, you have different torques, different RPMs, and then you can run a certain scenario and see what the sound is inside the vehicle. So that's probably, for example, for hybrid electric vehicles where really how the vehicle behaves depends on the state of charge of the battery. That's quite valuable to really be able to run these special operational scenarios. This was a part related to system MVH prediction, where I explained how frequency-based substructuring can be used once we have characterized noise sources to do these predictions for your full assembly system. Then we come to the summary. So I've shown how you characterize the sources. Once you characterize them, we can put them in the library, and then you can make assemblies, do predictions, and eventually even do your target setting, do modifications to see how you can improve noise and vibration. What are the advantages? I think if you're a supplier or if you are a car manufacturer, so if you are responsible for a certain component, you have some independent quantities to quantify different components next to each other for the NVH performance. You can do predictions virtually inside the vehicle and see if the component behaves as it should. And of course, this way of working, this process facilitates a lot of communication between the integrator and the supplier of a component. So the supplier can give independent load description data, and the integrator can give more realistic NVH design targets using this method. Okay, so this is what I wanted to show in this theoretically a bit dense session.